Hey guys, it's well, I'm preparing the test right now. I'm making progress, but we haven't talked about chapter 10 yet. So we haven't made any videos about it, and I haven't really talked about it. And so in lieu of the upcoming test, I thought, what a great time to talk about chapter 10 and make sure that you know the things that I want you to know that are going to be on the test. Okay. And so I want to do a little bit of a review. I think many of you already did the homework for chapter 10. Um, and if you haven't done the homework for chapter 10, then cat is this is going to help you. Okay? So, all right, let's get started. Alrighty. Okay. So, um we're going to talk about conservation of energy. Okay? So this is chapter 10, and I'm going to tell you the things that I think are important for the exam. Okay. One of the first things is you need to know about conservation of energy. Okay. And this is a really important concept for what we're doing here. Okay. Uh, Conservation of energy is the idea that if a system has a certain amount of energy, that energy can never be destroyed or lost, okay, if it's a closed system. Okay, so for example, let's say that you have, let's use a Pokemon. Okay, so let's say that Pikachu, okay, is traveling this way, and let's say he's moving pretty fast. He's going 30 meters per second. Okay. And I think, what is Pikachu's mass? Okay, let's say, the mass of Pika, the mass of Pikachu, um, well, I better look it up. Right. All right. The mass of Pikachu. Let's see, what is it? Okay, now we know. The mass of Pikachu is 6.13 kilograms. What a nice Pikachu. Cool. All right. 6.13 kilograms. Okay, so if Pikachu is an object made out of matter, which let's just assume that Pokemon are made out of matter. Okay. And Pikachu is moving at 30 meters per second. We could calculate how much energy he has. Okay. Because if you're moving, then you have a certain amount of energy. Okay. So, and kinetic energy is the energy of motion. So if you're moving, you have a velocity, then you have energy as well. Okay. So, how do we calculate kinetic energy? Of course, kinetic energy is it has the units of joules. Okay. And we can also write joules as Newton meters. Right? So 1 joule is a Newton times a meter. And we'll get to that in a little while where these units come from. But for kinetic energy, let's plug in to the formula here, 1/2 mv squared. So Pikachu's mass is 6.13 kilograms times his velocity, which is 30 meters per second squared. Okay, and so now we can calculate what Pikachu's energy is. All right, where is MATLAB? Oh, I closed MATLAB. Oh man. All right, well, We're gonna throw this into the old MATLAB. All right, let's share my screen. All right. MATLAB. Here we go. All right. So Pikachu's energy is 1/2 times 6.13 times 30 squared. All right, so this is Pikachu's energy, and I'm gonna put this in long form. Oh, it still gives me. All right, well, um, so that is 2.7585. Now, like short better. Okay, so let's do short. All right, there we go. All right, so 2.75 times 10 to the power of 3. Okay, so that means the Pikachu. Wait, let me stop sharing my screen here. Pikachu has a kinetic energy of 2,700 and 58.5 joules. Okay, so Pikachu's really moving. Okay, or we can write this in kilojoules, which is 2.76 kilojoules. Okay, so that is the energy of Pikachu's motion. Okay, and Pikachu will continue to have this motion. It doesn't have to be Pikachu. I mean, it could be a Falcon. Let's talk about something that's real. I know I always talk about Pokemon. Okay, but let's say if just a Falcon is flying here. Okay, so here's my Falcon. It's tail feathers. Okay, this bird is flying at 30 meters per second. Okay, the Falcon is going to have a kinetic energy of 2.76 kilojoules. Okay, that's the energy of the bird, and unless friction acts on it, then it will never lose any energy. Okay, and this is related to Newton's law because Newton's law tells us that things continue to stay in motion unless they're acted on by an outside force. Okay, so let's look at another example. Let's make an example here of a skateboarder on a half pipe. Okay, when I was younger, sometimes even now, I like to ride my skateboard. I think I shared a video of me riding in the parking garage. That was fun. Okay, so let's say our skateboarder starts up here. Okay, and he's gonna go down this way. All right. Now, um, the energy here, kinetic energy, it does not have a direction. Okay. And that's really important because kinetic energy is a scalar. Okay. It's not a vector. Ke is a scalar. Okay. And that's what makes this so convenient is we don't care what direction they're moving. Okay. Only if they're moving, then they have kinetic energy. Okay, now the other kind of energy that one of the other kinds is potential energy. Potential energy. Okay, so potential energy, right? And one of the really common ones that we're going to talk about a lot is pot gravitational potential energy. Okay, and gravitational potential energy is the force of gravity times the mass. So m times g. G is acceleration due to gravity on the surface of the Earth, and then times the change in height. Okay, so for example, if um, if my skateboarder starts out up here, okay, so and we'll call this we'll say that this is some height here, h. Okay, so we can call this down here. This will be we'll say that y equals 0 down here. And then I think these half pipes are about 3 meters, so we'll call this y equals 3 meters up there. Okay, so that's 3 meters. All right. So in that case, we could figure out how much energy, potential energy, the skateboarder has when he's up here. Now, when I say potential energy, because if if he gets released off the top, that potential energy is going to change into kinetic energy, right? Because gravity is going to pull him down, And so when the skateboarder's at the bottom, his velocity is going to be pretty high. Okay. Um, and when he's up here, when he starts out, all of his energy is in potential, and down here it's in kinetic energy. So if I asked you, well, what is the velocity of the skateboarder at the bottom? Right? We could compute that now. Okay. So let's do a little example here. Okay. mg times h. Let's figure out what his change in potential energy is going to be. And let's say, um, yeah, we'll say that the mass of the skateboarder, okay, so M equals 70 kilograms, right? That's what we're going to put in. G is 9.81 meters per second squared, right? And then H is 3 meters. So we'll put, yeah, H equals 3.0 meters. Okay, so we can plug in our numbers here. So we're going to have the mass first. Okay, so we'll have yeah. So we'll have 70 kilograms times 9.81 meters per second squared. Okay. Times the change in height here, and that is going to be 3.0 meters. Okay. Um, and so we can kind of figure this out. Let's just say that this equals 10, okay? So that gives us 700 times 3, so that gives us 20 yeah, 2,100, and we have kilograms times meters per second squared times meters. Okay, well, this stuff right here, okay? That is just a Newton, right? And then we have a meter over here, so this is Newton meters, or we end up with joules, okay? So this is my potential energy that the skateboarder has, okay? Now, if I said, all right, um, here's the height of where the skateboarder starts, these 3 meters. Calculate the velocity of the skateboarder down here at the bottom. How would you do that? Okay, well, this is really important because um, what we're going to say is, okay, that for the skateboarder, the kinetic energy at the bottom has to equal his potential energy at the top. Okay, we're ignoring friction, okay, and wind resistance. Okay, so we um, ignore friction and we ignore drag. Okay? So ignoring friction and drag. This statement has to be true. The kinetic energy at the bottom has to equal the potential energy at the top. Okay? Now, so let's plug this in now. Okay, we're going to do it symbolically, but we can say here 1/2 m times v squared. That's our kinetic energy has to equal m times g times h. That's our gravitational potential energy. Right? And so if we want to know what's his velocity at the bottom, all of the potential energy over here is going to become uh kinetic energy. Okay. Now what's really interesting, right, and is kind of profound is that the masses cancel. Okay. So for our skateboarder, okay, this kind of proves that your velocity of you going down this, it does not depend on your mass. Okay? All right, so now we're gonna solve for V. Okay, so I'm gonna multiply both sides by 2, multiply both sides by 2. Okay, so my 2's cancel over here. And so now I'm gonna get V squared equals 2 times G times H. Okay, and now I'm gonna take the square root of both sides here. Take the square root of this side and the square root of that side. Okay, well, the square root of v squared is just v. So this gives me v equals the square root of 2 times g times h. Okay, so then my velocity at the bottom, it only depends on the height that my object started out at. Okay, so I can put this in here. So I'll say V is going to equal 2 times 10. I'm just instead of 9.81 meters per second squared. This is easier. Times the height, 3 meters. Okay, and I forgot all the units. I didn't put those in there. Okay, but oh well, we can add them in because G had meters per second squared. Okay. Oh, and that's good because look at this. We're gonna get meters squared over second squared. That's all under the radical here. So it's gonna be meters per second, which is what we want. Okay, so 2 times 3, that's 6 times 10, that's 60. Okay, well, I know that the square root of 49 is 7, and the square root of 64 is 8. Okay, so we're going to get the square root of 60 meters squared per second squared. Okay, well, uh, yeah, I'm just doing this in my head. Okay, so that's closer to 64, so it'll probably be the square root of 7.6 meters per second. All right, well, that's just kind of what I what I guesstimate there, but let's check it. Let's check it. All right, what is the give me the square root of 60? Okay. Oh, 7.7. Okay. I was close. It was all right, so I said 7.6. All right, we got instead it was actually 7.75, so this is actually closer to 7.8 meters per second for my velocity. Okay. But it was yeah, it was close-ish. All right. So, um, but this is a really important lesson here. Okay. So basically when my guy's up here, okay, all of the energy is this is my skateboarder, okay? All of his energy is in the form of potential, but when he goes down to the bottom, it's all in the form of kinetic energy, okay? And so what would happen is this guy would keep going up here, and so my skateboarder would get back up here, and he would go to the same height that he started over here. And if there was no friction, he would just go forever. And there's actually a really cool video game that you can check it out. Okay, let's go to Google PhET skate park, energy skate park. Okay. So I will share with you my screen. Okay, this is a fun video game. Okay, because all right, here is yeah, here's my intro. Okay, so here's my skateboarder. All right, this is such a fun video game. And basically, what's going to happen is I'm going to put my skateboarder here. Okay. And if there's no friction, I can set my friction over here. I'm going to choose the cat. Okay. My cat here is going on this ramp. Okay. And the cat will just go forever. And over here is a plot. Okay. This is my kinetic versus my potential energy. Okay. So I'm going to go in slow motion here. Okay, when the cat's up at the top, all of his energy is potential. When he's down at the bottom, okay, so up here at the very tippity top, right there, all of his energy is potential. I'm gonna let him go down at the bottom. Okay, there's a little lag, but down here at the bottom, all of his energy is in the form of kinetic energy, and it just goes back and forth basically forever, uh, um, without any friction. Okay, so now I'm going to add a little bit of friction. Now, right here, we see the thermal energy is 0. There's no thermal energy because I didn't set any friction. So I'm going to turn on a little bit of friction. Okay, I'm going to do I like the pie chart here. All right, where's my pie chart? Pie chart. Oh, there's the pie chart. Okay, So see, the red one is his thermal energy. And as he goes back and forth, that thermal energy is growing. Okay. And I just have a little bit of friction here. Okay. But as he continues to go on, his thermal energy is going to grow and ultimately his kinetic and potential energy shrink. And that is, if there is friction, then it is not a conservative system. Okay. Now, let's turn off the friction. Once the friction is off, then you stop losing any energy. Okay. So that thermal energy goes away. Okay. And now it will just go back and forth. Okay. So with no friction, the cat will go forever. With friction, then you start to get therm lose. See, I'll turn my friction way up here. Okay. So if I have a lot of friction, then the cat's gonna lose steam and it will come to a rest very quickly. Okay. So for the test, this is going to be very important. There's a bunch of problems that ask you, okay, um here's some problem. Maybe it's a falcon or something on a ramp, and it says, okay, what is the kinetic energy going to be because of the change in potential? All right. Oh, so look, all of my energy was gone basically in the form of thermal energy, and the cat has stopped moving and it has zero kinetic and zero potential energy. So the motion has stopped. All of our energy is gone. All right. Let's look at another problem because I know that there's some of these on the test because as I said, I'm making the test right now, and it really is like the practice test. So definitely do those problems before you take the actual test, okay? Let's look at the case of if we're gonna do just one more example here, okay? All right, let's look at something on maybe it's a box on an inclined plane. And okay. So, let's say there's no friction, okay? And let's say our box starts up here at the tippity top. Okay. And all right, let's say okay, our box is going to slide down here to the bottom. Okay, it's going to go all the way down here. And let's look at the case of no friction at first. And let's say here that our angle is theta is going to equal, say, what's that? It looks like about a 20-degree angle. Okay. And this could be like a Pinewood Derby car. Okay. Did you ever do Pinewood Derbies? I love Pinewood Derbies. My son's not in Boy Scouts anymore, but oh man, the Pinewood Derby is probably the coolest thing ever. All right. So you start up here and this track up here, let's say that this is let's say it's like 4 meters long. Okay, I don't remember what it is exactly. Okay, and then over here, yeah, let's say this flat part here, let's say this is like 5 meters long. Okay, so all right, and if you don't know what a Pinewood Derby car is, it's basically just a piece of a wooden block, and you put wheels on it. Okay, and then you can make it smaller. You can do all kinds of things on it, and oh, do I have my Pinewood Derby car? Oh, yes, look at this. Oh, made a goblin one. Okay, here's my Pinewood Derby car. Well, look at that thing, man. That is oh, geez. Wow. Whoops. All right. Anyways, got my goblin car here. Okay, and I think I actually yeah, this is my car, definitely. Okay. I painted this cool goblin on it. All right. Definitely the goblin doesn't make it faster. Okay. What does make it faster, see, my car is very thin because if you decrease the cross-sectional area, you decrease the drag. Okay. So you want to make your car thin, right? Want to make it thin. Because remember that the force of drag, okay, is um Hey Siri, what's the force of drag? All right, so the formula for the force of drag is 1/2 times the density times velocity squared times the coefficient of drag times the area. Okay, well, as your area starts to decrease, okay, the force of drag goes down, which is why, and you can actually just think of this as like a constant, so we'll call it K times A. Okay, the thing that you have control over is A. All this other stuff is, you can't really control that. Okay, so if you make A smaller, your car will experience less drag and you will go faster. Okay, drag does act like a non-conservative force and takes energy out of your system. All right, but let's not worry about drag right now. Okay, so the length here is L equal 4. Okay, so if I ask you, what is the velocity right here when you get to the bottom of this ramp? How would you do it? Okay, and this is important for the tests. Okay. Um, so let's think about how you could calculate what the force of drag is. I know what the distance here is my car. And if you look at it, that is the hypotenuse of a triangle. Okay. And so what you want to find out is you want to say, all right, how much height did it change? Right. And so how much energy did I get from potential? Because for this car, okay, um, all of the energy comes from potential. And let's actually go back to the app here. Okay. So here's our thing. We're gonna go to Energy Skate Park. You can customize it. You can make your own. Yes. Look at this. I'm gonna make my own Pinewood Derby track right here. Boom! Oh, we're doing it, man. Yes. Okay, I am making a Pinewood Derby track right here. This is gonna be totally amazing. Okay, there we go. Got a nice flat slope there. Okay, we want a pie chart of our energy. Okay, and we're gonna put, oh no, stop. Dang it. Okay, putting this up here. All right. So where is our pie chart? All right, yes. So see right here. All of our energy is in, and we'll turn off friction. All right, we got no friction. All right. So at the top of the ramp here, all of the energy is in the form of potential. Okay, and I'm gonna go slow here so we can slow this down. All right. When I hit start, wait, I want to, yeah. Then the Pinewood Derby car goes down to the bottom here. Okay, and uh all the energy has turned into kinetic energy. Okay. So we have our speed increased, okay, and we lost potential energy. Okay. So this doesn't give us any numbers, okay, but this is just good for basically getting the concept of it. All right. So let's put our Pinewood Derby car over here. We're gonna change it to a dog. All right, here we go. Here's my dog. No, I want a cat because I have a cat named Zeus. Okay, there's our cat. All right. So we're gonna release Zeus on the Pinewood Derby car. Okay, so he gets over here, and all of the energy is right there. And now, once Zeus is on the flat spot here, okay, you'll notice that the our kinetic energy does not change because there is no friction. Okay, and so that means that whatever the velocity of Zeus is over here. Zeus will have the same velocity over there. There's no more acceleration. Only right here. Okay, so here we go. Right. So Zeus has gone down. Once Zeus gets to the flat spot, the energy does not change. We can here, yep. Let's get this nice big figure here. Okay, so Zeus is going up at the top. Put this there. We're at the bottom. All right, that's good. Okay, so we'll make this really flat. Okay, so we'll let it go. So Zeus's energy changes from kinetic to potential, and it continues onward. Okay, and it doesn't change. Now let's do it with a little friction here. We'll turn up this friction. Okay, and we'll start at the top. But now when we do it, okay, the thermal energy is going to start to grow. Okay, and that takes away from the speed that you hit. And then when you get on the flat spot, okay, the velocity is decreasing, kinetic energy is decreasing because friction is taking it away. All right, we've got everything that we need to calculate this now. So let's find the actual velocity here based off of these parameters. Okay, so this is the hypotenuse of my triangle. This is the opposite side. I want to get this height. Okay, so we're going to go back to trig and we're going to say that um, from my trig, y over x, no, y over r, the hypotenuse. Okay, so y over r, my hypotenuse equals sine of my angle theta. Okay, so then I can use this to figure out what y is. Okay, so I'm going to say y is going to equal r times sine of theta. That's going to be my change in height. And so now, okay, here's my equation for potential is going to be mg times h. Okay, and so I'm going to plug this. I'm going to plug it in right here to h. Okay, because we just determined that this is equal to r times sine of theta. So, or L, I call it L. Okay, so we'll plug that in. We'll say, all right, U is equal to mg times, and that's, I called it L. Sorry, I'm switching the variables around, but it's basically L times sine of theta. Okay, so this is my potential energy. That's how much energy I have when the cart starts up here at the top. And so I want to find the velocity down here at the bottom. So I just need to set this equal to the kinetic energy, or 1 half mv squared. Same thing we did before. Okay. And again, the masses cancel. Okay. So now I'm going to solve for v. I'll multiply both sides by 2, multiply over here by 2. Okay, my 2's on this side cancel. This 2 cancels here. Okay, so I end up with v squared equals g, or 2 times g times L times sine of theta. And then I'll take the square root of both sides. Take the square root of this side and the square root of that side. That's going to give me v is equal to the square root of 2g times L sine of theta. Okay, so what's my velocity going to be here? Well, let's go. Let's go throw it into MATLAB and we will find out. All right, MATLAB. All right. So I have, okay, the square root of 2 times, no, I don't need an emoji, 9.81 times the length of the ramp. So the hypotenuse of my triangle. See, I got a triangle right here. Okay. And that's going to be 4. Then times sine of d, because this is in degrees, sine d of 20, close bracket with my square root there. Okay, and this is going to give me my velocity. All right, my velocity then is going to be v is going to equal 5.1809 meters per second. Okay, or my velocity will be 5.2 meters per second. All right. So we did it. I found the velocity up here, okay, that the Pinewood Derby car would be traveling as it reached the bottom of the ramp. Okay, so um my my cart started up here. All of its energy was in the form of potential. Okay, and I went down here and all of my energy um turned into kinetic. Okay. All right. Let's talk about what potential energy is. And let me do a little demonstration here. Okay. Oh, yes. All right. Now, let's talk about potential energy here. Okay. So Charizard, okay. If Charizard is right here, okay, and I raise him up, okay, I had to apply a force to Charizard. Okay, it took me energy here to raise up Charizard. Okay, I had to use my muscle and lift him up. Okay, and I gave him energy. Okay, and now when I move my hand, okay, gravity is gonna start doing work on Charizard. Okay, so watch this. Right. Let's see all that potential energy that I gave him. This morning I had hash browns, okay? I took that energy contained in the hash browns, okay? And it had some eggs too. Hash browns and eggs. Okay, so I converted that chemical energy. See, I'm using hash browns and eggs energy, okay, to raise him up. Charizard. So that energy that I got from eating that moved my muscles, and now I'm giving him potential energy. Okay. And if I move my hand, all of that energy now becomes kinetic. Now, where does the energy go once he hits the floor? Well, maybe you heard a thump. Okay, I heard a thump. Uh, some of that energy goes into deforming him, and he's like, right when he hits the ground, I like, but Charizard doesn't mind. He's not actually a Pokemon. He's a stuffed animal, so he doesn't actually care. Now you might say, why do I have all these Pokemon? Well, they were actually my son's Pokemon. Okay, but why is it always never wants to focus on the Pokemon? But whatever. All right. So now, um, if you have a car, then because we need to talk about energy. Energy is responsible for the lights being on right now, right? If I turn off this energy, it's dark, right? So if I turn on the lights, that takes energy. What's creating that electricity? Well, somewhere they're burning coal, or maybe a windmill is turning and generating electricity, okay? Something is moving, and that movement gets converted into electrical energy with magnets, okay? And that's kind of a physics 2 thing, okay? But that electricity that's created from something that's moving, in the case of coal, right? If you're burning coal to create electricity, hey, what's happening is you burn the coal and you basically boil water. That's what you're essentially doing. As the water boils, it gets turned into steam, and it's a lot of steam. And steam has um, a lot of pressure, okay? And so if you have a closed container and you boil it, right, the steam that's created from the water will move the lid. If you put a pot of water on the stove and you boil it, um, the steam will knock the lid off of it. It has a lot of force, and it can turn a turbine. That turbine has wires that move across the magnets, and if you have a wire that moves across the magnet, the electrons start to move, which is what creates electrical currents because they're charged particles in a magnetic field. You need magnets to create electricity. Okay. And so, um, if you have, say, an electric car, right, you can charge the battery with electrical power. Right? Maybe you have a hybrid, right? Hybrids are really cool because it actually converts some of your kinetic energy into electrical energy. So if you have a hybrid, if you step on the brakes, right? There are magnets in your brakes, and there's a coil, and it takes some of your kinetic energy and it charges the battery, right? Because think about that. Normally, when you're driving your car, you step on the brakes. where does your kinetic energy go? Well, it goes into basically heating up your brakes, right? There's friction. And so all of your kinetic energy gets converted into heat and you slow down, right? Just like the thermal energy we saw in the skate park, and that energy gets dissipated into the environment. It's not destroyed, it's still there, but you just can't get it back and do anything useful from it. If you drive a hybrid, it takes your kinetic energy and it uses it to charge the battery, right? Because normally you just lose that energy. And that's what makes hybrids so efficient is um, you convert your kinetic energy into electrical energy, which you can use again. So pretty smart. Okay. Now let's talk about water heaters. Okay. Is it better to have an electrical water heater or a gas powered water heater? Right? Because you're thinking, okay, there's the difference between these, okay, is that basically if you have a gas-powered water heater, right, natural gas comes into your house, you burn it, and you take that heat directly and you heat up the water, right? And so you are, at your house, you're creating the heat, you're taking that heat and raising the temperature of the water. That takes energy. If you have an electrical water heater, okay? In that case, you're burning coal at the power plant, you're creating steam, you're generating electricity, and then you're sending it over a really long wire. Okay? That process is only about 35% efficient because a coal-fired power plant or natural gas-powered plant can only be a maximum of 30 to 35% efficiency. That means the rest of your energy is just gone in the form of heat. And that cannot be improved because of the laws of thermodynamics. Right? Now, if you have a car that's gas powered, right, guess how much gas or energy in the gas actually goes into moving the car. Maybe just actually write down a number on a piece of paper. Okay? Do it right now. Um, so the actual efficiency of cars is about 20%. That means that all the energy that's stored in the gas, only 20% of it goes into actually moving your car. The rest of the energy just makes your car really hot, right? If you ever gone to a gas station and checked your oil after you've been driving, your engine's usually over 100 degrees. It can burn you. Truck drivers cook brisket on it. You can put it in your motor. I don't know how they do it, but they use tinfoil and put a chunk of meat in there. The motor will cook it. That's how hot it is. You're burning gas. Most of that energy is just radiated into heat. Okay? Electric cars aren't that way. Hey, they're 90% efficient. But here's the thing. If you are burning coal to charge your electric vehicle, that does not save energy, right? Because you know, burning the coal to make the electricity is only 35% efficient. Okay. Then you have to transmit it over a power line. But then again, your car is only 25% efficient. So, actually, it's not that bad. So, now, if you use solar panels or wind to charge your electric car, that's great, right? Sunshine is free, and there's basically an infinite amount of sunshine. If we can convert that into electricity, we don't need to burn fossil fuels, right? If we could take all of the sunshine that hits the United States in one day and store that energy, we could power the United States for an entire year, right? That's without burning coal, right? Just from solar energy. So, something to think about. Windmills, right? The wind blows, creates electricity, doesn't add any carbon to the environment. It doesn't actually hurt a lot of birds, right? That's actually not true. Okay, it's not harmful to birds for the most part. Yes, occasionally can a bird fly into it? It's possible. Usually more birds fly into your windows, right? That's a bigger risk is birds trying to fly through windows. Um, No CO2. Okay? Same thing with hydroelectric dams. You have water that is at a much higher position. The water falls down through the dam, and its potential energy becomes kinetic energy, and then you use that to turn a turbine, and you make electricity. Uh, no pollution there. So you don't need to make CO2, okay? We don't actually have to do it, right? If we had solar panels and wind, you don't actually need fossil fuels. Now, there probably is a place for those. It's nice if you want to go on a big trip or, in an emergency, you can use gas. So, we could have a few gas-powered cars for emergencies, but we don't need to anymore. We could have electric cars for everything. Now, it does take some energy to build the batteries and make the car, but after 10 years, you're saving energy, right? You're using much less energy. Um, Thanks for watching this video. There will be more videos about chapter 10 and the test will be online soon. Thanks for watching.
Thank you, like and subscribe down below.